Hello everyone. This is a session that I'm recording for the revision of numerical methods and optimization techniques. We're looking at the fifth unit today. We are starting with the fifth unit and we'll slowly move towards other topics of fifth unit in this revision session. In this session, in previous session, which I have also uploaded on the YouTube, the link will be provided to you. uh, we finished with the classical methods of optimization. The classical method of optimization is a simple method in which we take the first and second derivative test. The first derivative test helps us in identifying the points at which the extrema could lie, and the nature of the extrema is then decided by the second derivative test. So that is what we did in the previous revision lecture. Now, what we are doing here is that we are going to start with the next part, the numerical methods of optimization. As discussed in the class earlier, there are different types of methods that are used for optimization problems. Broadly, we can divide them into four different parts. The first part is the classical method or analytical method, which we studied, which is about taking the first derivative and the second derivative test. The second group of methods is called as brute search methods. So in brute search methods, what you do is you basically start putting the values of x in the function, or whatever the variable is, you start putting the values in the function, and then you try to find the values over a range of certain values. When you get the minima or maxima, whatever is required, that you can set it as minima or maxima in those problems. So that is brute search methods. The third category of methods that we are studying is called as gradient methods. So gradient methods are the methods that depend upon a gradient. So what is a gradient? Gradient is nothing but the first derivative of a function or slope of a function. So any method that depends upon the slope or the first derivative, those are called as gradient method. Technically, classical method is also a gradient method, but here specifically in gradient methods we are looking at the method that use numerical methods rather than analytical methods. The third case is gradient methods. The fourth case that we're looking is the important one for us, that is region elimination method. So what a region elimination method is, that we keep on looking for a value of a function at certain points in a particular interval. And once we get the functional values at that point, we eliminate a certain region with a surety that your extrema, that is maxima or minima, is not lying in that particular region. So those are your region elimination methods. Now what do we study in this? Four different methods. In classical methods, it is the classical method that you have studied, which contains necessary condition and sufficient condition. The second, brute search method, we are going to look at exhaustive search. In the gradient based methods, we are looking at Newton's method of optimization. And then in the fourth part, which is the region elimination method, which is important for us, in that we are going to study three different methods. The first one is bisection method or interval halving method. The second one that we are going to study is uh, golden section search method, and the third one is Fibonacci search method. All right, so today we are going to look at the classical method. So before going into that, what is optimization? So optimization, mathematical optimization, is the selection of the best element. So it is the selection of best element in a particular uh, the selection of best elements with some criterion from a set of available alternatives. So there are a lot of alternatives available for us. Each of them may satisfy our condition that we have, but our point is we are trying to find the best out of them. What is the best possible scenario out of a given situation? That is what we are trying to study, and that is called as optimization. Now, optimization problems of all sorts arise in various quantitative disciplines. So, they are present in computer science, they are present in engineering operations, to operations research. They are present in economics. They are present in development of solution methods in mathematics, and they have been along with us for centuries. Uh, Example, you can say Let us take the example of Amazon today. So what happens with Amazon is that they have warehouses present at certain areas in the city or in a country, and they want to provide products to various part of the country through those warehouses. So let us say that they have warehouses located at Pune, they have one warehouse located at Hyderabad, and let's say they have one warehouse located at, let's say, New Delhi or Noida. Now the question arises that if an order is placed from, let's say, Jaipur or somewhere in Madhya Pradesh like Jabalpur, which warehouse should the company Amazon send the product, so that the delivery time, the costs are minimum. So these are nothing but optimization problems. The solution is present. You can send the product from three of those warehouses, any of those warehouses. Okay, the problem can be sorted that way. But our aim is to minimize the cost, minimize the time. So based on that, we start looking for different methods. You start looking for the transport modes that are available from Noida, the transport modes that are available from Pune, the transport modes that are available from Hyderabad, and then you look at the various costs and a time that are present from there. And based on that, you can select the appropriate warehouse. So that is nothing but a simple example of optimization. In simplest case, like I said, the optimization problem consists of either maximizing or minimizing a real function by systematically choosing input value within the allowed set and computing the value of the function. So allowed set in our previous example was that there are only three warehouses. There are warehouses in Pune, Hyderabad, and Noida. You cannot, ship the product from Jaipur, or you cannot ship the product from Bhopal because it is closer to your Jabalpur. You have to set you have to send it from your warehouses that are present in your cities. So that is the allowed set from which you have to choose the best option. Okay, so that is nothing but optimization. The generalization of optimization theory and techniques and other formula constitute a large area of applied mathematics. All your applied mathematics techniques are based on optimization. Like I said again, same thing. More generally, optimization includes finding the best available values for some objective function given in a defined domain, including a variety of different types of objective function and different type of domains. The example again I have given you the same thing. Now we'll start with the classical method of optimization. So how do we start with classical method of optimization? Let us say that we have this function here shown in the graph. Okay, so you have the blue line that represents the graph. So you have this blue line which represents the graph. All right. So here you can see that there is a certain high point. There is a high point here. There's a low point here. So these points are nothing but your extremas. Okay. So this is a maximum point. This is also maximum point, and this is a minimum point. Since there are many maximum points, you call this as a local maxima. That is the maximum within a certain region. Similarly, this is a local minima, which is a minima within a certain region, and this is also maxima within a certain region. If we plot from infinity to infinity, minus infinity to infinity, whichever has the maximum value, the point which has maximum value, we call that as global maximum. And similarly, the point which has the lowest value, we call it as global minimum. All other maximas and minimas are called as local maxima and minima. So at these points, okay, so these are the points which we have to find out. All right. So how do we find out? These are the points where your slope is flattening out. Okay. If you see that, if you draw a slope at that particular point, it is a straight line. It is a flat line. So this is the point where your slope is zero. So at your maxima or your minima, whenever you draw a line, it's a straight line, and therefore this, excuse me, and therefore this tangent is called as, but this tangent has a slope equal to 0. So how do you find out a line that a slope is equal to 0? This, in very simple words, you find out the derivative of that particular function. So if you find out the derivative, that is where you get your extrema of a function. Okay, your you also get a tangent at certain point. They are called as saddle points. These saddle points are the places where um, the function just changes from maxima to minima without having a certain maxima or minima. So that is called a saddle point, and we are not worried about saddle point. Saddle point is not a point of extrema, it's just a point of curvature, and therefore we do not consider them as extreme points. Now, this classical method depends upon two different conditions. First one is called as there are two different criterias on which you can base this classical method. This classical method, the conditions that are called as they are called as sufficient conditions and necessary condition. Necessary condition first, and then sufficient condition. So, what is necessary conditions? If function f of x is defined into interval between a and b, that is x lying between a and b, and has a relative minima or extrema at a particular point, so instead of minima you can say extrema at x is equal to x star, where x star is also lying between a and b, and if the derivative, that is derivative of the function f dash of x, exists at x is equal to x star, then that derivative is equal to 0. So in very simple words, at any particular point, we looked at the graph previous point, at any extreme point, if you take that derivative of that particular, it should be equal to 0. First thing, it should exist and it should be equal to 0. Alright, so because like we said, like I showed you in the graph previously, at that particular point, the slope becomes a tangent to the curve. So that line, the tangent, will always have slope equal to 0, and slope means nothing. Slope is nothing but your derivative, the first derivative of the functions. First derivative of the function should be equal to 0. That is the necessary condition. Second thing is sufficient condition. Now what is sufficient condition? Now let us say that you have first derivative of x star is equal to second derivative of x star or third derivative of x star up to the n minus 1 derivative of x star is equal to 0, but the nth derivative of x star is not equal to 0. Right, so this is minus, sorry, there's a mistake here, this is n minus is equal to 0, but the nth derivative of x star is not equal to 0, then f of x is a minimum value if the nth derivative is greater than 0 and n is even, is a maximum value if nth derivative at x star is less than 0 and n is even, and if n is not even, if n is odd, then it is neither maxima nor minima. So this is nothing but your sufficient condition. Okay, so when I say even, so it should be second derivative, fourth derivative, fifth or sixth derivative, eighth derivative, and so on. All right, so if you keep on finding the derivatives, if the first derivative is 0, second derivative is 0, third derivative is 0, and fourth derivative is not equal to 0, then we check if the fourth derivative is greater than 0. If it is greater than 0, then it is a minimum value. If it is less than 0, then it is a maximum value. But for example, if third derivative, even if fourth derivative is 0 and fifth derivative is not 0, alright, then it is neither maxima nor minima because n is odd, because it is the fifth derivative. So that is nothing but your optimality criteria. So these are your necessary conditions and sufficient conditions. Now based on this necessary condition and sufficient condition, we can find out the maxima and a minima of a particular given function. So what we'll do is now we'll do some numericals. To solve some numericals, keep in papers, pen, pencils, calculators with you handy. We are going to require them as we solve this problem. What I'm going to do is at every particular step, I'm going to give you some time in which you're going to calculate it yourself and then find out the answer in the video. Okay, so always keep your pens and calculators handy. It will be useful for you. Now this is the question that is given to us. Determine the maximum and minimum values of the function f of x is equal to 12x raised to 5 minus 45x raised to 4 plus 40x cube plus 5. And you have to find the maxima or minima, that is the extreme points of this particular function. So I'm giving you a minute about 30 seconds to write this down. So write down this question that is on a rough on your page, and we'll solve them together. Quickly write down this question, then we'll continue. Alright, so now moving forward, how do we solve this? Just think about it. How do we solve it? We use the condition, the criteria conditions that are given to us. The first one is the necessary condition. So what is necessary condition? The necessary condition states that if the derivative exists at a certain point, it should be equal to 0. So we are going to use that. We are going to find the first derivative of the function. The first derivative of this particular function is 60x raised to 4 minus 180x cube plus 120x square. So this is the first derivative, and we are going to equate it to 0 and find the value of x. Okay, so I'm giving you about 2 minutes now. Please equate this to 0 and find the values for x. Use your arithmetic knowledge that you have. One of the methods that you can use is substitution method. Put x square is equal to, let's say, capital X. That is one method. The second method that you can use is take x square common. So if you take x square common, it will be x square into bracket 60x square minus 120x plus 120. You can also take 60 common, so 60x square outside the bracket. Then inside the bracket it will be 60x square into x square minus 3x cubed plus 2, 3x plus 2, x square minus 3x plus 2. So what should be the values? Can you tell me? Yes, going to give you a couple of minutes. Just 20 seconds more. Can you find out? Yes, the values of x are 0, 1 and 2. So you have three different values. There are actually two zeros, 0, 0, 1 and 2. So we'll just take three values, 0, 1 and 2. So these are the points. From necessary condition, like I told you previously, we can find out the points at which the maxima lies, or extrema lies, not just maxima, it could be maxima or minima. So extrema lies at these 3 points, that is x is equal to 0, x is equal to 1 and x is equal to 2. So at these 3 points your extrema is going to lie. So that is, now from the necessary condition we can just tell whether where the extrema lies. We cannot judge the nature of these extrema, whether it is a minima, whether it is a maxima, or whether it is a saddle point. So that can be done only with the second step, that is the use of sufficient condition. So now go to second step, which is sufficient conditions. So in sufficient condition, what do we do is we first find the second derivative of this particular function. So what is the second derivative? The first derivative we have already found out. From that we are going to find out the second derivative of this particular function. So first derivative was 60x raised to 4 minus 120 or x 180 x cube plus 120 x square. So that was the uh, that was the first derivative. From that we're going to find the second derivative now. So second derivative will be equal to 240 x cubed minus 540 x square plus 240 x. So this is your second derivative. Okay, so now it's a simple derivatives thing that you have done, you have studied earlier. All right, so derivative of x raised to n is n into x raised to n minus 1. The same thing we are using here. All the powers are reducing by 1 and you're multiplying the coefficient by the power. So your second derivative is 240 into 240 into x cube minus 540 x square plus 240 x. So these are your derivatives. Now going forward, we put the values of x that we have found from necessary condition in the second derivative and then find the functional values. So based on those functional values, we are going to judge whether it is a maxima or minima. So first point, let us say that x is equal to 1. Okay, so I'm going to give you a minute, put x is equal to 1 in the function and find the value. Alright, come on, I'm giving you about 30 seconds. You can do it in 30 seconds. Put x is equal to 1 in the function and find the value of the when I say function, I'm talking about second derivative. Put x is equal to 1 in the second derivative and find the value. So f double dash of 1 will be equal to 240 x cube. So x cube is nothing but 1 cube. 1 cube is 1, so that will remain 240 itself, minus 540 into x square. X is again 1, so x square is also 1. So 540 into 1 plus 240 into x, x is 1, so therefore 240 into 1. So that becomes 240 into 1 minus 540 into 1 plus 240. So that is 240 minus 540 plus 240. So that is 480 minus 540. So that will give you at the value of second derivative at x is equal to 1 will be equal to minus 60. So minus 60 is the value at x is equal to 1. So based on this, what was the condition? What were the conditions? If the derivative that we're finding is even, so here n is even because this is second derivative. If second derivative is not equal to 0, okay, first derivative was equal to 0, second derivative is not equal to 0 because it is minus 60. Okay, so n is even, it is not equal to 0, then the condition is that if it is less than 0, that means it is a point of maximum. So since n is even and f double dash of x is less than 0, x is equal to 1 has a relative maxima or local maxima, relative or local. So local maxima is also called as relative maximum. So at this particular point, there is a relative maxima. Now, condition for the second value at x is equal to 2. Okay, at x is equal to 2, we are going to find out the value of this particular function. So I'm giving you a minute, find the value of second derivative at x is equal to 2. At x is equal to 2, please find the derivative value. So it becomes 240 into 2 raised to cube minus 540 into 2 square plus 240 into 2. So 2 cube, you know it is 8. So this becomes 240 into 8 minus 540 into 2 square. 2 square is 4. We know that. Plus 240 into 2. Alright. So basically the equation becomes 240 into 2 cube 8. So that is equal to, how much is it? 240 into 8. So 240 into 8 is equal to 1920. Is that correct? 1920. That's correct. Minus you have 540 into 4. So 540 into 4 is 1080, 1080, plus you have 240 into 2, which is equal to 480. So if you solve that, you get the value as plus 240. So the derivative, second derivative functional value of second derivative at x is equal to 2 is 240. Now again, since n is even and f double dash of x is not is greater than 0, therefore x is equal to 2 has a relative minima at this particular point. So the value at x is equal to 2 is a global, or sorry, is a local minimum or relative minimum. Now the third point of x at x is equal to 0. If I put x is equal to 0 in the second derivative, what do I get? Okay, so I get f double dash of x is equal to 240 into 0 cube minus 540 into 0 square plus 240 into 0. So basically a 0 cube is 0, 0 square is also 0, and anything you multiply by 0 becomes 0. So therefore, by second derivative test, f double dash of x at x is equal to 0 is 0. Now in our sufficient condition, it is said that the last was the derivative. We can state whether it is a maxima or minima only if the derivative is not equal to 0, if any particular derivative is not equal to 0. So here second derivative is equal to 0. So what we do is we go to the find the third derivative. Okay, so we find the third derivative. What is the third derivative of the function? So it becomes 720x square minus 1080x plus 240. So that is the second derivative. Sorry, so that is the third derivative now. So now at this third derivative I'm going to put the value of x. So x, if I put x is equal to 0, what I get is 720 into 0 square, which is 0, minus 180 into 0 plus 240. So 720 into 0 becomes 0, minus 1080 into 0 also becomes 0, plus 240. So the value at x is equal to 0, the functional value for third derivative at x is equal to 0 is plus 240. So now, since it is positive number, okay, so what is the condition state that it has? We can only we can only say whether it's a maxima or minima if n is even, the derivative is even. But this is the third derivative and therefore it is an odd derivative. So since n is odd and and the third derivative of x is not equal to 0, we can say that at x is equal to 0, it is a saddle point. So what is a saddle point? It is a point of neither maxima nor minima. So that is a saddle point. It is neither maxima nor minima. So this is how you solve a problem by classical method. So you have the first derivative and second derivative. The first derivative is called as necessary condition. From necessary condition, you find out the values at which the extrema could lie. So you take the first derivative, equate it to 0 and find the values for x. That will give you the points at which the extrema lies. Then you make use of sufficient condition to find the nature of this particular point. So what you do is you take the second derivative and equate it to 0. Sorry, don't equate it to 0. You take the second derivative and put the values of x that you have found from your necessary condition and find the functional values at that particular point for second derivative. Now if the second derivative is not equal to 0 and if it is less than 0, then it is a relative maxima. If it is greater than 0, it is a minima. Now if the second derivative is 0, you find the third derivative. If the third derivative is not 0, we can say that it is a saddle point. But even if the third derivative comes out to 0, then you can go to the fourth derivative. If fourth derivative is not 0, first derivative, second derivative and third derivative are 0, but fourth derivative is not 0, then again you can use the conditions. Since n is even, you can use the condition. If it is lower, if it is less than 0, it's a maxima. If it is greater than 0, it's a minimum. So that is how you use these conditions. These conditions are also called as Kahn-Tucker conditions, KKT. It has different names. So this is an important question that can come in the exam. So sometimes this question can come as a theory question as well, asking you to state the condition or optimality criterion for optimization of a single variable problem. So this is what you use. With this, we'll stop here. In the next lecture, we'll solve a few numericals on this together so that it will be useful for you. Thank you.